Our next talk of this event is by Flavio Cirillo, who's from NEC, Germany. So he's going to talk on edge data analytics. So I'll give a brief intro to Flavio. So
Yes.
Flavio Cirillo is a research scientist of the IoT research team at NEC Labs Europe, Heidelberg, Germany. His research topic includes situation-aware analytics and IoT analytics platforms, focusing on cloud, edge, federation, privacy, data usage control aspects, mainly in the scenario of smart cities. So he is the maintainer of open projects, part of the 5-ware network covering the IoT backend layer. He is a member of the IEEE, ACM, and the ComSoc. So Flavio, it's great to have you talk at this event. So thank you for agreeing to talk. So I'll invite you to start your talk.
Yes. Yeah. Can you see my screen now? Oops.
Yes, Flavio. Yes.
Yeah, I need to open the slides. Okay, and you can hear me, right? Oh, fine.
Yes. Yes. Go ahead.
Okay. So good afternoon, everybody. Thanks for the introduction. So the presentation of today, it will be around the edge data analytics platform, mainly on the, and then I will introduce the background where the presentation we will work around is the hyper-connected IoT, and I will present an environment of smart city with a multi-party scenario. We will see like a specific use case, just as an example, would be an automotive use case in urban environment. And then we will see how the edge data analytics can be handled with which kind of solutions. And we will see like four main features, like the decentralization, federation. And then that of decentralization means from the cloud to the fog to the edge, and federation means different domains of instances, so different verticals. And then we will see like the features of data flow management, service management, and data usage control that needs to be applied on both decentralized and federated system. We will see like mainly the two approaches, which we will be intent-oriented. We will explain you later, and standards how in order to have like a system working with a multi-party scenario. And then we will have takeaway for this course. So mainly, what I mean like multi-party in case of smart city. So nowadays, like we have different verticals, for example, in 5G. And then we have, for example, automotive industry or whatever, e-health or whatever. For example, for automotive, we can have augmented autonomous driving through IoT sensors. Of course, like the automotive vertical doesn't have the IoT sensors themselves, but maybe they could use surveillance camera or like traffic light that are handled by a different domains, by, for example, like homeland security or by the city traffic system. Or like we can have public safety applications that might be handled by, I don't know, city governance, and then we might use digital signage for steering crowds in case of a public emergency. And also in this case, it is needed data from other domains. I don't know, like cars, for example, like or and having access of advertisement digital signage. And this kind of shared ecosystem can be happening also like in supply chain, where there are multiple companies working together. So what is hyper-connected IoT in this case? Normally we think about verticals where there are devices that are getting data, and this data is stored in clouds that are single in the enterprise cloud of single domain, and applications applied on these clouds. So usually we have a many-to-one linkage of sensors, because like it's a single cloud using their own infrastructure, and then one-to-one linkage between applications and cloud. So it's really separated in silos. But we are going towards, like also with 5G and with like network slicing, we are going towards an hyperconnected world of IoT, where the same information from the same devices are used, or same information providers are used by different clouds, and the services are in a kind of holistic, so using this data in a kind of holistic manner. So we are going to have a many-to-many linkage from with edge computing, and also many-to-many linkage between services. So like a service in the mesh up and information mesh up. So speaking about network slicing of 5G, then we have that in a single silo, we have the data that is gathered by the devices, integrated and managed in in the in the same network slice, we can say, and then the services are orchestrated by this silo, for example, like in the automotive, in its stack, so between the fog, the edge, and the cloud. And on top of it, there are applications running, services running, like data enrichment or serverless computing um, uh, for some intelligent applications, and with abstraction of digital twin. But this is for a single silo. If we need to have more than, so like in have a connected IoT, we will have multiple slices of IoT that needs to communicate with each other, both in terms of data that needs to be exchanged, and also in terms of services. So like the service migration and service handling needs to be done horizontally between silos, and also but of course we need to take care about the security, the privacy, and the data usage control, because of course a company that spends money on having their infrastructure and their IoT data and service, they want to have full control of the effort and cost. So they want to have possibility to have a holistic service, but they want also have full control of what they possess, so their data and their service. And we will go a bit later on what means data usage control, and we will introduce later, which is in the next slide, I think. So data sharing is what I said. Single different domains need to share data with each other. So we are going from a centralized data analytics that is based on a single silo from the same devices owned by the same company, from a data sharing approach where analytics is done on a second domain, for example, domain B, using data from a different domain, domain A. When I say domain, it means like administration domains. So for example, two different companies. And this topic is pretty important nowadays. For example, in the European Commission strategy, with the launch of Gaia X project, which was launched at the beginning of 2020, exactly for the idea of creating a joint collaboration between companies for sharing data towards, for example, standards and service exchange and privacy and control. So I've seen that we are moving towards a multiple organization system where data is not anymore centralized in a single system, but is federated, because maybe you might get data from a different service in a different domain and use it in your domain with your application. The data is coming from multiple providers, so it's not anymore a single silos. And of course, the environment is not anymore trusted, because there are different administrations, and then there will be peers of systems. And therefore, the trust between the companies is an issue here now, because they need to handle services and data, and give data outside, which may be a problem for the secrets of the company, or anyway for not sharing costs or something. So in this case enters data usage control problem, which goes beyond the access control of data. So access control is like to provision data at the present time. So it controls who can access data, for example, authenticated user or authorized user, under certain circumstances. But what happens after the data is shared? So in the future, so you need to have obligations. So like, for example, you cannot use data if not anonymized. This is like a usage control. I give you data, but you need to anonymize or you need to do something before using it. So there are constraints on what happened after data is shared. For example, like a consumer can read the data or can even can read but not process, or maybe can process only for a specific purpose. Can process the data only if this data is pre-processed, for example, anonymization, or post-process. So after that is processed, it needs to go for some aggregation, for example. And for example, the data can be processed, but only remotely. So instead of sending data towards the domain, the service is sent towards the data, so that the data cannot exit, but the service is applied locally where data is. So we can see some requirements from this, like because in this scenario we have a bit complex handling of services and data. And it is important to have a system that decouples data analytics development with the data analytics process management. So it's the developer of an analytics service does need to hard code where the data is executed in the whole system, in the between the fog, the edge, and the cloud, and also between the domains in for example, fog element of a different domain. Then it's needed an automatic orchestration of data management and the decentralized execution, again, in fog, edge, and cloud. And it should be automatic. It should be decided by orchestrators. There should be a federation of peers and a way to have a peer communication, and also like a kind of distributed intelligence for orchestrations of data and data management. And finally, it should be another usage control that should work among this federation and among the decentralization of the single silos. Let's take an example here with multiple domains. A single example of automotive. So let's assume that there are car owners that has data, that have their own data of electric cars. They might share data with the manufacturer of their car. For example, I don't know, the car manufacturer has the stores locally the data. And there is an external company, for example, electric vehicle charger company, that is interested on having optimized their parking spot with the EV charger column, having information from the car data. For example, they want to get the information of geolocation data in order to understand distribution analysis of cars in real time in the city. And then also information about the battery status of the different cars, in order to understand, it estimates when a car needs to be recharged, maybe also predict when and where a car is going to park, also considering distribution analysis, and also getting information from the parking spots itself of electric car charger in order to have let's say, updated estimation of the charger status, in a urban environment. But now, what happens if the car manufacturers wants to apply some policies on top of this data? For example, anonymization of data. They don't want to have the name of the users being shown in the data from so exposed to an external company, and also that the data should be analyzed. So the anonymization, for example, should happen before the data is shared. So should happen within the car manufacturer the domains and the execution environment. And what happens then if we have now a second car manufacturer that might share data and even apply new data usage policy? Of course, the management of the service needs to be handled dynamically, also with the new providers appearing. So we have two main challenges in this case, like a high complexity when dealing with dynamic data processing flows, because of course, if the data, the processing is already happening up and a new car manufacturer is joining, it's tough to handle these with hard-coded deployment, and a policy enforcement to be considered not only after but also during the construction of the data processing flows, because for example, like its dynamic placement of the services in fog, edge, and cloud and the different domains needs to happen, also depending on the situation of the different execution nodes and the data coming. So we go to have an intent-oriented approach. What means? It means data provider has their expressed their intent on how the data should be used, no matter who is going to use and which kind of analytics is going to be applied. And the data consumer just describes its data analytics without knowing who is giving the data and where this data is coming from. So um, the providers and the consumers is expressing this with a simple usage policy specifications and service modeling in case of the consumer, and the system itself needs to have a logic and intelligence to match these two intents from both sides, and then having the orchestration, service management, and data management happening automatically. Let's see how we specify a policy model, which is, for example, so it's very easy. So this is what we implemented. So the policy just expresses like who is data provider, which data this policy refers to, which is the target of this policy. It can be a single, specific other domain, or it can be any, so to any other domains. For which purpose? So you specify, for example, a specific data service, or like you can also put any, and then you specify specific constraints. For example, like you specify a rule, like anonymization, and you give also some parameters. Here are examples of these policies. And in the case of anonymization, we see that the car manufacturer is always like the one specifying the policy, since it's the data provider for the type of car, addressing any consumer for any purpose, and of course the data must be preprocessed before used with anonymization. Or we have a second policy like fenced. Fenced means that data needs to be cannot exit as it is out of the original data provider, but the data processing needs to come inside the execution nodes of data providers for example, in this case, anonymization or any kind of processing. Of course, for example, this policy is pretty hard to be applied before by the data consumer, because they will never know who is the data provider and where to place the execution execution task. We will show you how that will happen in the use case we presented. The service model will be also quite simple, and it's mainly like to describe the service. So you have a topology of service which is made of functions, like for example, Rabbit functions, putting together in a topology with input data and output data. So intimate data used by these Lambda functions, and then it's specified like where these where the service should be applied, like in which scope. For example, like in the same domain, globally in all the federation, or in another external domain. Some service level objective, like you want to optimize latency, accuracy, or like a cost, and priority. Like for example, it's a critical service, you want to have exclusive usage of some execution node, or like inclusive, like you want to have it handled, for example, by a Mac, Etsy Mac orchestrator. The service, so this service model, how then is used, how is translated by the crowd and edge orchestration and in general from the federated orchestration. Once the template of the IoT service is given, we've seen is like pretty abstract. We just have like a list, a topology of functions with the kind of data you need as input. Is given by the system, which you understanding also the usage context, also the usage control, understanding also which scope to use, so in which location, for example, this service needs to run in a specific town, for example, like in Berlin in Germany or like in Tokyo in Japan. And then the system should, the cloud edge orchestration should create an execution plan. Execution plan comes out from the generic topology and is, for example, deciding to have multiple um, multiple tasks to be deployed because of, for example, going close to some to some data generator, for example, close to cameras or close to cars. So you have like some more instance of the same task. And then this information is this execution plan is translated in a deployment plan. In deployment plan where where each task is executed in the different execution nodes. Um, the data is also how the data flows between tasks is also quite tough to be decided beforehand. So before an execution plan is decided, so the system is automatically brokering the data between providers and consumers, where each task can be can be seen as producers in case when data is created. For example, like we've seen before, when data is created, intermediate data is created here, but also consuming data for getting input data, intermediate data, or like raw data. And there is a central IoT broker that discovery data, and with a second component that has a view where the data is located, and dispatch data automatically in a context aware. So which kind of data is inside the message. So it's not anymore topic based, but it's more content oriented, because it's not it is not based about the geographic scope, or like about some threshold or some other filters. We use for these some standards, which is given by ETSI, which is the European Standard Institute, and the standard is called NGSI, and we have a new standard release, which was NGSI-LD. And this standard is adopted by the Fireware framework, which is like a big open source framework in Europe that I think is also used in India and in Japan. The orchestration of service is done by a system called Forkflow. Also, in this case, this is like a Fireware component. It's open source, and you can use whenever you like, download and use it. And there are three main components: service management, context management, and data processing. This we have seen, but data processing is exactly where is like an abstraction of where the task is executed in each single execution nodes. And the whole system here, or like a sub set of these components, are run in different elements on the stack of cloud edge nodes and device. This is a single view of a domain, but as a domain can communicate with another domain in terms of data with another federated broker with a domain B, but also the service orchestrations is handled in a kind of distributed approach. For example, service orchestrator can communicate with each other to exchange commands on starting task. So we see what means service orchestration here, the actions. We have the first four, like add task, remove task, add input, and remove input, which is locally of the service orchestrator towards like the local computing nodes. Computing nodes can be in the fog, it can be the edge and the cloud. Here's generic computing node. and the service orchestrator commands the computing nodes to start a service, a task, a specific task. But when a task needs to be run remotely because the task cannot exit, so the data cannot exit the original data provider, for example, domain A, then it's used a send task, where a task is sent remotely to the other service orchestrator, but then take decision where locally the service is executed in the edge, or in the cloud or in the fog. Let's see an example how this happened with the automotive use case we showed before. Let's assume that we are in the policy enforcement, so we are in the domain here, service orchestrator of the electric vehicle charger company, and you get that this EV charger company wants to run this service. The policy enforcement then discover where the data is available, so it gets data that about e-car data, get back the policies with this e-car data, and then with its logic decides some atomic action. For example, change the topology to put a preprocessing task before the data enters the EV charge analytics, send to the data provider the data remotely, because we've seen like you can send the data, you can send task to a remote entity. This because we have the fenced data. Instantiate locally the task in the EV charger company itself domain, and then you can schedule in the straight instantiation because of time to live here. We didn't explain here before, but you can have also kind of dynamic instantiation and destruction of task. We have implemented the system, as I said, with Fogflow, which is a system that you can download in open source. And then we use blockchain for the communication of data availability and policies between systems. This is because we want to go towards data and also of service execution. So it is important to have a kind of blockchain approach. You can also then in future we also target to have a kind of marketplace, and so an ecosystem with a market backed by a marketplace, and the tasks are Dockerized. So we use Docker for Dockerizing tasks. Well, so we have also implemented this and tested the use case that I've shown you before, and we have had 3 domains, so 3 separated domains with the different workflow, and the task, so the service that has been instantiated has been deployed in different domains from different workers handled by different domain. For example, the anonymization that was not even given in the original service intent is deployed in the car manufacturer A and car manufacturer B instance of execution nodes. And then only the data that is anonymized is given out to the service. And then it's the data is analyzed on the EV charger company side. We have also done some kind of understanding of how much this is helpful in terms of complexity and how much helps on the complexity side. And we've seen that if we have an approach like our intent-oriented approach, we need to define few elements, like in terms of policy, functions, and links. If instead, if we consider like a flow-oriented approach, where you need to specify the low level of attaching its and so every task instantiation between each other. And of course, if we go to have a more complex system with more data providers, more policies, and more even services, so we have, for example, essentially two services, two same services, we see that in total, the number of things to be configured in the intent-oriented approach is 11 elements, while 4 times as well in case of manually instantiated and deployed system. Of course, if you go to to increase the number of data providers, we see that our system in intent-oriented is scales pretty well, besides the number of policies that each data providers needs to write their own policies. While if you want to scale the service, we see that the number of things to be configured is always the same. While if you have a flow-oriented approach, it scales very much. So this is just to conclude. We've seen that it is needed to have a decentralization of IoT deployment across the whole service computing stack, such edge, fog, and cloud, and there should be a decouplement of analytics development and analytics management. It should be a federation of centralized IoT system by management by diverse parties, and context management and service management should be done automatically using standardized approach like NGSI and FireWire. And you should have like an intent-oriented approach for reducing complexity and also for having a preventive and proactive for handling the dynamicity of the system. With that, I will conclude my presentation and hope if you have any questions, you can tell me now or send me a mail.
Thank you, Flavio. There are a couple of questions. I think I'll just post them to you and maybe you can. So the first question is, current public cloud services such as AWS, Azure, and Google Cloud cannot be used to implement the cloud segment of the future smart city scenarios. Do we need a different type of cloud?
So AWS, they offer already an IoT stack for AWS or Microsoft Azure. The problem is that they are not. They are kind of vendor lock-in, so they want to have the full stack with them. If we want to go with the full IoT solutions of this big cloud, which is very useful in terms of simplicity of using, but it's tough then to have like a federation of peers. While if you use the cloud itself as a mere infrastructure, like in terms of machine, then you can apply on top of it like the overlay of FireWire, for example, and then using this overlay architecture, you can have, for example, cloud of AWS or cloud of Microsoft working together. We have done this. We have done this work, for example, with 8 cities in Europe, where there were a cloud of different providers, and we applied this overlay architecture on top of it in order to have them working together.
Thank you, Flavio. Actually, there are a few more questions, but I think since we are running out of time, we are ahead of time. So I think we'll probably try to answer them in some way. Probably we'll consolidate the questions and provide answers to the participants.
I can try to answer now in the chat if they are in the chat. So
yeah, I think that they are on the Q&A box. Flavio, yes, they're on the Q&A box. Yeah. Thanks a lot. Thanks a lot. So Flavio, thanks a lot for the very informative talk. And thanks for agreeing to talk to us. A great talk. So thanks a lot.